My name is Brian Cousins. I'm the chair of the Department of Earth Sciences here at Carleton. And it is a great pleasure to introduce my colleague, Dr. Jeff Pinata from our department, who's going to be talking to us about Yellowstone caldera today, which is a topic very close to my heart. Jeff did his PhD at the University of Southern California, then did a short postdoctoral fellowship there, and then moved to the University of Wisconsin at Eau Claire, which is primarily an undergraduate teaching school, a very, very good one. And it's here that Jeff really honed his teaching skills and his lab design skills, which is what got him to Carleton. We advertised for a lab coordinator position, and Jeff was far and away the best candidate for that. But Jeff has far exceeded that initial appointment. As you'll note, he's a contract instructor and an adjunct professor in the department as well. He's been teaching a couple of courses in our department, including a brand new one called Planet Hollywood, which is a survey of how science is both utilized and portrayed in both television and Hollywood movies. He also teaches our first year undergraduate course, which has an enrollment of well over around 300 or so, which keeps him very, very busy. And his recent adjunct appointment means that he'll be supervising students on their honors, BSc honors projects, and potentially graduate projects as well. Now, Jeff has a fantastic background in all of the earth sciences, not just what he specialized in for his PhD. Hence his presentation today on Yellowstone caldera, which is probably the most active magmatic or volcanic system in North America, and possibly the most dangerous one, is a terrific topic. And for those of you who might remember, the Discovery Channel, I think this was about maybe 15 years ago, kicked off its fall season with a really great combination of a documentary and a made-for-TV movie on an eruption at Yellowstone. And so Jeff is now going to bring us up to date on what we know about Yellowstone today. So Jeff, take it away.
Thanks, Brian. Yeah, sorry for the late start, but I'll try and keep this down so that we're not going over the sort of allotted time. But yeah, this is an interesting topic that I've taught a lot about and been to Yellowstone, but I want to preface this by saying that it is not a place that I actively do scientific research in, but I do research in the area in Montana, in southwestern Montana, and actually through the West. But I'm using Yellowstone as an example that I know very well as well, but as an example of how science can be communicated and how misconceptions are come up in science. And it's this science communication topic that's kind of been something that's been interesting me for a number of years, and I haven't done a whole lot with it. Until, as Brian mentioned, I just decided to teach this and develop this course called Planet Hollywood and start really thinking a little bit more about how science is being communicated. And so that's why we're here today to talk about Yellowstone. And I actually debated about whether I would use, the San Andreas Fault or some other earth science topic to kind of go down this road. But Yellowstone is definitely something that's fun and interesting, and I know quite a bit about it. So I decided to go with Yellowstone. And before we even get started, before we even move off this title slide, I just wanted to point out that this is the abbreviated title that got sent out to everybody, which is a very enticing title. Did you know that Yellowstone caldera is going to erupt with catastrophic global consequences, which again is this kind of a doom and destruction type title, but in fact it wasn't the title for this talk that I decided on. So this is the title of the talk that I actually have for the talk. So the first part, did you know that Yellowstone caldera is going to erupt with catastrophic global consequences? ? Possibly, not likely. Yellowstone Hotspot science and communicating that science to the public. So I have this obnoxiously long title, maybe even a little bit confusing. which is pretty common in science to have, our research science topics and titles that are not really that enticing for public consumption necessarily. So, so this was really fascinating when I saw the communication by the Faculty of Science with this abbreviated title. I was like, oh, that sounds a lot more enticing than my title for sure. And I completely did not plan that. So, so part of what I want to talk about today is, in fact, the science. I don't want to just talk about science communication in this. I do want to talk about the science, because one of the ways I think that we effectively communicate science is by actually doing a good job of actually describing the science and giving that science to the public in a way that can be digested. So I definitely want to talk about Yellowstone, but I'm going to interject at a few points some of the ways that we are communicating science and the risk, in this case, the risk, because this is obviously, a volcanic eruption not only involves science, but there's a public policy aspect of things like Yellowstone and San Andreas and so on and so forth. So we want to be able to actually communicate not only the science, but the risk as well. But what we're going to do today is we'll talk about what is Yellowstone, the magma generation. I don't know how many of you know much about Yellowstone. We'll talk a little bit about the plate tectonic settings, what is a hotspot, and then what are the hazards? What are the volcanic and the hydrothermal hazards at Yellowstone, and then some of the more recent science in terms of how do we actually know that there's magma below Yellowstone and that this is in fact an active system, which it is. And then again, I'm going to interject and kind of at the very end, hopefully leave some time for how do we do this? And to be totally blunt, this is a topic that I'm really just kind of getting into and thinking about how to generate some data and how to think about, researching science communication, not about actually communicating the science. I think I've done a fairly decent job of that through my past, but researching that science. So I'm going to leave you with more questions than answers when it comes to the communication part, and that's for sure. But again, some food for thought. And welcome some of the feedback that I'm sure I'll get on this. But so let's start off with just a very basic, some introductory material about volcanism and Yellowstone and thinking about how we get volcanoes. So these are some of the geologic settings that we get melting in the earth such that we can produce volcanoes. And so we have more or less four main geologic settings. We have mantle plumes, okay? And those are in fact what are responsible for places like Yellowstone and Hawaii and other places around the world. And that'll be kind of one of the main focuses of this talk, obviously, because we're talking about Yellowstone. The Cascades, which is another location, but this is a location where we have subduction. So we have a downgoing oceanic piece of lithosphere that is subducting beneath the edge of North America, and that leads to volcanism. Well, it leads to partial melting of our mantle, and it leads to volcanism. We have mid-ocean ridges, okay, where we have spreading of our oceanic lithosphere that produces partial melting in the mantle. And great examples, the Mid-Atlantic Ridge that runs right down the middle of the Atlantic is a great example of this. Or we can have rifting, like the early stages of this Mid-Atlantic system would be actually a continental rift, where we also can get melting, and we have this actually throughout the Western US as well. We have rifting, ongoing rifting. Other places like the East African Rift Zone as well as another place where we get that. But the key aspect in all of these situations is that magma is generated by partial melting of rocks within the mantle and the crust. And the key thing in red here is the concept of partial melting. And this happens under specific physical and chemical conditions that I'm not going to go through right now. Take a first-year introductory earth science class, and we'll go into more depth about this. That's for sure. But the key is that we get partial melting, and I want to pause here for a second to kind of come back to science communication, because in thinking about this topic and in thinking about communicating science, one of the lessons I learned early in teaching was to be honest, open, and intentional about misconceptions. And as scientists, no matter what field we're in, we all know about the misconceptions. It's those things that frustrate us when we talk to people about science, or we're listening to the news, or we're listening to even reputable sources talk about a particular topic, but they get something wrong. And so as an example, I paused here because this is a perfect example of people, by and large, and by people I mean basically non-geologists and even some geologists, get this concept of melting in the earth incorrect. By and large, people think that a vast swath of the Earth's mantle is molten, is a liquid. And that's just flat out wrong. What we're talking about here, and the key aspect of this in red is partial. We're usually talking about single-digit percentage, 3 to 5% melting, maybe upwards of 10% melting in these different geologic settings to get the magmas and the lavas that are producing, the igneous rocks in these different settings. And so that's something that I'm very transparent about. And when I teach or when I engage with the public about a topic, is being open and intentional about identifying those misconceptions. When I teach first-year geology, I say this is something that you will almost certainly have heard before, and that is completely wrong. That the mantle is all molten, and it's a hard thing to get out of people's heads. But I think by being open and honest about that, it's a good first step to actually let us understand better the science that goes into whatever topic we're dealing with. So I always identify misconceptions. So let's come back to the science. So let's think about what a hotspot magnetism is. And I didn't look at the list of attendees, but if Richard Ernst is one of the attendees, please close your ears and your eyes on this one, because this is an overly simplified view of what a mantle plume is. So if we think about the lithosphere, and here again, this is not to scale, but this is like the lithosphere. This is part of the upper mantle in the Earth's crust. All right, the rigid part of the Earth that we all are living on. And what a mantle plume is it's a solid but flowing part of the mantle that's rising up from great depths. And these are some fluid dynamics experiments, some old photos, but that just give the shape of these mantle plumes really well. So they rise up from great depths, and we can talk later about why and how this happens. There's a bunch of different mechanisms, but regardless, we know that these mantle plumes exist, and then they're rising up from deeper within the mantle. And as they get to higher and higher levels, they have this sort of mushroom cloud kind of shape. This is a dense fluid flowing through a less dense fluid flowing through more dense fluid. But as they rise up, they get this mushroom shape. And then eventually, as they get really shallow in the Earth's crust, they undergo some partial melting, and then we get some magma produced. And in this case, we get if we partially melt the mantle, we get this composition called basalt, and we get these flood basalts that pour out. And we can also get some other products, but I wanted to inject flood basalts into this conversation right here, because we'll talk about those with respect to Yellowstone soon. But the idea is we get a mantle plume, and this is our hotspot right here, right at the surface. This is where all of our volcanism and activity is happening at shallower levels within the crust as we get these partial melts rising up through the crust. So in the case of Yellowstone, what is going on? Well, in the case of Yellowstone, we have very thick continental crust and upper mantle, so a big thick slab of lithosphere. And here's our mantle plume, rising hot but solid. Notice again, a lot of people think that liquids, but it's not liquid. Rising hot, solid asthenosphere or mantle material that rises up, and when it gets to relatively shallow levels, we produce melt. And that melt, again, is basaltic in composition, and part of that melt can rise up and actually erupt as a volcano. And in the case of other hotspot areas like Hawaii, for example, that's exactly what's happening. That mafic or basaltic magma is coming up and rising up through the crust and erupting in places like Kilauea and the other Hawaiian volcanoes. But in the case of Yellowstone, where we have this really thick lithosphere and thick crust, some of that magma, that basaltic magma, ponds or pools in the crust, and we can actually partially melt. Again, I use the word partial here intentionally. We can partially melt the crust, and we get a much more felsic or less iron-rich magma called rhyolite or rhyolitic magma. And this is the stuff that makes Yellowstone the topic of much of the doomsday theories and much of the realistic concern for eruption are these rhyolitic magmas, because they are very viscous, they're loaded with gas, and they're exceptionally explosive, which is why we care about Yellowstone so much. But this is the basic geologic setting for what's going on underneath Yellowstone. Again, this is a nice textbook view. I'm going to show you the kind of modern scientific view of what's going on based on some recent research later on, but I want to set the stage for that first. So these are our Yellowstone magmas. So what do we get? We get basalts and rhyolites out of these continental hotspot systems. And so what does that look like? Our basalt is iron and magnesium rich, loaded with iron and magnesium rich minerals, and it's generally dark in color, okay? And our rhyolitic magmas, in contrast, are very iron and magnesium poor, but silica rich, which is the silica in these magmas are what causes them to be very viscous, or at least in part what causes them to be very viscous and able to trap gases. And that's why these silica rich and iron and magnesium poor rocks are indications that we need to be concerned about Yellowstone. And just for completeness, sitting in the middle is another type of magma, andesite. This is kind of what we would expect at our subduction zone volcanoes, which are those that are on the west coast of North America, from California all the way up through Alaska, and then all the way around the Pacific Ring of Fire, including in Japan. Okay, but what we're dealing with are basalts and rhyolites, and what we're really concerned about are the rhyolites. So let's take a look at the general geologic setting for the Pacific Northwest of the United States and the setting for Yellowstone. And the Yellowstone hotspot, right now sits way over here in westernmost Wyoming and parts of Montana and Idaho as well. Yellowstone National Park sits up here in this corner. And I should point out right now, if you've never been to Yellowstone National Park, you should absolutely plan to do that at some point in your life. It is spectacular. I am not going to be able to do just due diligence here in this seminar, and you really should just experience it for yourself. So that's my push to go visit Yellowstone National Park. But what we see here in the Pacific Northwest are a couple things. We do have a subduction zone over here. We have the Pacific Plate being shoved underneath the edge of North America, and that leads to a chain of volcanoes, Mount Shasta, all the way up through Mount Baker and a whole bunch of other Mount St. Helens. If you're old enough, you probably maybe even remember Mount St. Helens. Okay, but these volcanoes, these red triangles, are associated with that ongoing active subduction. Okay, they don't have anything. Yellowstone doesn't have anything to do with that. Yellowstone is a result of that mantle plume, and that mantle plume started rising up and getting to a point where it could start producing partial melts around 16 million years ago, when it produced a big basalt flood event called the Columbia River basalts that sit right here in Washington and Oregon. And so we have this huge plateau of basaltic lavas that outpoured from these vents as the initial outpouring of magma from this Yellowstone plume. And then through time, we have two different types of materials being erupted from this hotspot. And they are these red areas, which are these big rhyolitic volcanic fields, okay, Yellowstone being one of those fields, okay, that we can see dotted all along here. And notice the age progression from about 60 million years all the way to about 630,000 years ago, which was the last major eruption from Yellowstone, which we'll come to here in a second. But underlying that in Oregon and Idaho and most of the active volcanism in these gray areas are basalt. Some of those basalts that are partial melts of the mantle are still coming out. There are active volcanoes in this part of the world right here, Craters of the Moon National Monument, eruptions that are less than 1,000 years old in this part of the world. Okay, so we have both basaltic magmatism and rhyolitic magmatism associated with the Yellowstone hotspot track. And as I mentioned, the age progression here, I want to point out the last 3 eruptions. And these last 3 eruptions are the ones that, we hear about a lot and are part of the story, the news stories that come up related to Yellowstone, because the last 3 major eruptions occurred at 2.1 million years ago, 1.2 million years ago, and about 630,000 years ago. Okay, and so if you do some quick math on that, 630,000 plus 630,000 is about 1.2. Okay, 1.2 plus 630,000 is about a little bit of more than 2 million years ago. So it would appear that the last 3 major eruptions, we can say that the last 3 major eruptions have this episodic nature of about once every 600 to 700,000 years ago. Okay, and with the last one being 630,000 years ago, that puts us within the window of opportunity if the pattern holds for a volcanic eruption. Okay, so that's something to keep in mind, and that plays into a lot of conspiracy theories and misinformation about Yellowstone, or I guess over dramatization about Yellowstone, and we'll come back to that point as well. But what we're going to pay attention to is just a little bit more on the geology of Yellowstone here. But one other thing I want to point out on this map, okay, is why we're getting this pattern. Well, we're getting this pattern because that mantle plume is relatively fixed. Right now it sits underneath Yellowstone, but the mantle plume didn't move. The mantle plume did not migrate in this direction towards the east-northeast through time, but the mantle plume is relatively fixed. Again, we can debate about this a little bit. There is some movement in the plume, but it's relatively fixed. But what is moving is the North American plate, and this blue arrow represents the direction that North America is moving. It is moving off to the west or west-southwest, and as the plate moves over this relatively fixed plume, we get this track of volcanism that follows it. Okay, so that's an important aspect of Yellowstone. So let's kind of get in and start thinking a little bit more closely about Yellowstone and the Yellowstone caldera. And I'm going to talk about what the heck a caldera is here in a minute. But for right now, what I want to point out is this kind of weird, it's not distorted, it's just at a weird angle, but it covers a chunk of Wyoming and Montana and a little bit of Idaho. And just I'm going to point out a few things for reference that we'll come back to in later diagrams and refer to. So the park boundary, which shows up on a lot of diagrams, is this yellow boundary right here, Yellowstone National Park. The Yellowstone caldera is this red boundary. Now, again, it's not always going to be red and yellow lines on the maps, but I just want you to pay attention to the shapes of these. Okay, so the caldera boundary is in red. And it is a big feature. This is this is like almost 70 kilometers across. So this is a really massive volcanic system. And within that volcanic system, we have many, many things going on. We have some of these domes. I want to point out these domes as reference, because these are areas where there has been some past volcanic eruptions, but there are also areas of active uplift within the Yellowstone caldera. And I also want to point out Yellowstone Lake, which in part falls outside of the park itself, but Yellowstone Lake itself is a nice geographic marker. And again, just for reference, here's the Snake River Plain. You can see the dark nature, great place to grow potatoes here in Idaho, but also a great place to have some active volcanism. So Craters of the Moon is up in this part of the world right here, where we have some active volcanism going on. Actually, sorry, Craters of the Moon is right up here, my apologies, where we have some active volcanism of the basaltic variety. But this is the locus of much of the activity for the Yellowstone caldera at present. So what the heck is a caldera? Well, a caldera basically is a large depression associated with a volcanic eruption. So this is specifically referred to a diagram that's referring to what's going on with Yellowstone, but we can have these same types of features, much smaller features, with any kind of volcano, whether it's one of those volcanoes on the West Coast or a Hawaiian Islands volcano. Generally, the volcanoes will have some kind of depression, or a lot of people use the term crater. This is another misconception. They're not craters; they are calderas. The calderas at the top of volcanoes. And so how that happens is when we have magma below the surface of the earth. Notice this is down deep within the earth. We have magma, and if it starts to erupt, or that magma rises to produce eruptions, we have a mass transfer. So we are transferring mass, in this case in the form of magma, from deeper within the earth to shallower levels or to the surface if it's a volcanic eruption. And therefore, we have to transfer some additional mass downwards. Okay, and so that's what happens. We get these big sort of ring-shaped faults and other faults that drop the rock that sits above that magma down as the magma gets ejected. And so here's what we see. We see this schematic depression. Okay, so we have higher topography around here and lower topography here, where we have this downdropping of the crust as the eruption took place. And then, of course, in the case of, a system like Yellowstone, we have additional magmatism and volcanism that's happening, uplift and other features. So that's what Yellowstone is. It is a very large rhyolitic caldera that has, again, erupted, large eruptions in 3 times in the past 2.1 million years. Again, 2.1, 1.2, and about 630,000 years ago. And so, coming back to that, so that's where we sit right here. That's that caldera that we see is formed by those 3 major eruptions in this part of the world. So now what we're going to do is we're going to hopefully that kind of sets the stage for what Yellowstone is. It is a big caldera system, rhyolitic, all right? But now let's take a look at what's going on, some of the products, the hazards, and the science behind Yellowstone. And then we'll think about that title again and how it gets communicated. So I showed a very basic view of what a mantle plume was, using some fluid dynamics diagrams and a textbook diagram. But one of the interesting questions, and it was always a question in my mind until relatively recently, the last sort of 10 years-ish, is how if these mantle plumes are so simple, why aren't we getting more basaltic magmatism in Yellowstone, and all of the basaltic volcanism is happening off to the west? And it turns out through a whole tremendous amount of research that was done mainly by the University of Utah's seismotectonics group, who have put out a huge array of seismometers that allow us to sort of image the interior of the Earth, the upper 100 to 200 kilometers of the Earth's crust and mantle through these big seismic arrays. They've come up with this more modern picture of what is happening at Yellowstone. And what I want to point out first is what's going on at the surface. So here's our Yellowstone caldera, again, roughly 65, 70 kilometers across. these two domes, the Mallard Lake Dome and the Sour Creek Dome. And then off to the west southwest, we had that eastern Snake River Plain where I mentioned there's some ongoing active volcanism. And what the seismic imaging is showing is a very interesting picture of the upper 100 kilometers of not only what's going on with respect to Yellowstone itself, but what's going on with respect to the Mantle Plume. So as we kind of go down through Yellowstone, what we see are, in the seismic imaging, are rhyolitic partial melts. And I'm going to talk more about these later on. So I'm going to just indicate that they're here. Okay. We also see tremendous evidence for a lot of hydrothermal fluids. So hot water, mostly water and carbon dioxide, but hydrothermal fluids in the upper part of the crust. Notice that that's a lot of stuff that's happening in the upper 10 kilometers, really shallow. And that this rhyolite is all in the upper 5 to 15 kilometers. And then at deeper levels, we have a region of basaltic partial melt, okay? And the interesting part, recall that I talked about North America moving off to the southwest, and it moves at around 2 centimeters per year. Doesn't sound like a lot, but that 2 centimeters per year motion leads to a drag on this mantle plume, and we end up getting this basaltic magmatism rising up through the crust and producing things like the craters of the moon and all the volcanism that makes up the eastern Snake River Plain, or the Snake River Plain. So this is a lovely new addition to the science that describes not only what's going on in Yellowstone spectacularly, which we'll come back to, but also the overall picture in the region for, you know, the bimodal volcanism, the basaltic and rhyolitic volcanism. So that's a really, really cool addition to the science through seismology that's happened over the past less than 10 years here. So again, just to come back to this view again, so that's kind of describing what's going on in this part of the world. So what's going on right beneath Yellowstone, but also that basaltic volcanism that's happening in these lighter gray areas here as North America moves over that fixed plume. But let's dive into what's going on in Yellowstone. And I should start off by saying that it is absolutely perfectly clear that Yellowstone is an extremely active system. And so all of the, regardless of whether you're out in left field doomsdayer type person promoting weird things on Facebook and YouTube and every other social media platform, or you're actually a scientist with the U.S. Geological Survey or National Park Service, everybody pretty much agrees, everybody agrees that this is an active system. So we need to pay attention to it, okay? It's not going to erupt tomorrow. I'm going to just throw that out there right now. I can guarantee with 100% certainty that we will not have a global catastrophe tomorrow from Yellowstone, because we have a pattern of products that we see at Yellowstone. And that's what this diagram is showing. We see the frequency, in very generic terms, more frequent, and then the destructive capability, which the things that we've talked about already are those big caldera forming eruptions that, again, every 600-ish to 700-ish thousand years, we get one of those big eruptions. But we also have things like lava flows, and we'll take a look at those. We have strong earthquakes. Not only do we have strong earthquakes, but we have, in this more frequent category, tremendous numbers of small earthquakes, as well as small hydrothermal explosions. So these are very abundant, in fact, daily at Yellowstone, these hydrothermal activity. The small hydrothermal explosions are really explosive, and there have been some relatively recent ones. There's several per century. But these are the ones that we want to be thinking about, these caldera-forming eruptions. And we want to be able to convey a message that we absolutely need to pay attention to these things as scientists and as policymakers, but we don't need to be panicking about it because we have indications as to when Yellowstone might become more active, which again, I will touch on here in another minute. But let's just go ahead and really quickly, since we did get started late, I'm going to blast through this stuff pretty quick. We're going to just look at these different features. So the geothermal features, in fact, are incredible. This is reason enough in and of itself to go visit Yellowstone. It turns out that Yellowstone has more hot springs, geysers, and mudpots, which are just basically hot springs mixing with loose material, mud. There are more hot springs, geysers, and mudpots in the Yellowstone caldera in Yellowstone National Park than the rest of the world combined. Okay, so this is a hot area. This is a big geothermal area. All right. And one of the most spectacular things are geysers. This is not the most famous, which is, of course, Old Faithful, which erupts about every hour and 15 minutes. This is from the Norris Geyser Basin. You can see people here. You're able to go and watch these eruptions if you haven't seen them. But these are happening all the time. All right. And very basically, geysers happen when we have geysers or hot springs. These things are happening because we have cold surface waters, rainwaters, and other surface waters that go down into the upper part of the crust. They're not touching magma. They're just getting in contact with hot rocks that are above the magmatic system itself. And as those hot water, as those waters get heated, they become superheated. They get heated up to 400, 500 and above degrees centigrade. And they then, of course, want to rise up, and they rise up and form hot springs and geysers and form these spectacular eruptions on a daily basis. And every once in a while, I have an image, every once in a while they do erupt a little bit more catastrophically, and I'll show a picture of one of those in a minute. But we also have somebody at my door, which is odd and unexpected. Let me just make sure that's not urgent. Oh, good, just package delivery. So we also have geysers, some spectacular, this is the Midway Geyser Basin. So again, you can see the boardwalks, so you can go and walk around and see these beautiful blue hot geysers and hot springs. You get this beautiful blue color because the water is extremely hot. And the blue light from the sun gets reflected the most easily. And so you get these spectacular blue hot springs. You also get some of this. You get some iron being leached out of the surrounding rock, which forms these iron deposits. And then the interesting thing about the green parts, many of the hot springs in and around Yellowstone are, at least the ones that are close to the public, are becoming green. And that's actually from people throwing pennies into the hot springs. And those pennies are, the copper is actually reacting and forming more green deposits. So don't throw pennies. Not that we have that problem in Canada anymore, but if you go and visit and you end up getting some US pennies, don't throw them into the hot springs. That's not cool. So hot springs, geysers. Again, here's just another up-close picture of that spectacular blue and clear water coming out of the hot springs. This is the Morning Glory hot spring. The other product that we get from Yellowstone are lava flows, and we have these rhyolitic lava flows every few tens of thousands of years. These are some of the more recent lava flows. You can see 72,000 through 164,000. These are big rhyolitic and sometimes a little bit of pyroclastic material, hot fragmental material. I'll show a picture of these next that are erupting. So we know we can go in and date these things. So we know that the system is active because of these other eruptions. Here are some of these eruptions. This is some obsidian. So obsidian is a common rhyolitic product. Here's some more obsidian and some more of the tufts, with little chunks of obsidian in this. You can go in and see these all over the place in and around Yellowstone. The pyroclastic material, or the hot fragmental material that gets erupted, as well as the actual lava flows themselves. And an interesting aside, just since we're talking about it, when I was at University of Wisconsin, I was colleagues with a couple, an igneous petrologist and an anthropologist, who did an interesting study on the obsidian from in North America. And it turns out that indigenous peoples used obsidian as to barter with all over North America. And much of the obsidian that is found in different tools, arrowheads and other cutting implements all over North America, as far east as New York State, I know, but a lot in Michigan as well, comes from Yellowstone. And so this was a very important area for collecting obsidian for cutting implements, and so that's a really interesting thing. And my two colleagues did a really cool geologic and anthropologic study on tracking this obsidian, both from the chemistry side of things and the anthropology side of the equation as well. But anyways, that's another topic in entirety. But let's come back again to the products. Again, what we see here, this incredible distribution of hot springs. So what we're seeing in black and green are all of these thermal areas. So these are the hot springs, mud pots, and geysers that we see all throughout this caldera system. Again, Yellowstone Lake and caldera boundary in black right here. So an incredibly active system. And it's also huge. I mentioned this before. This is a huge system, which is one of the reasons why we need to pay attention to it. I've already mentioned this. Yellowstone is gigantic. When it comes to eruptions, the size of Yellowstone is something that we really need to pay attention to, because many of you, or some of you, might even remember the Mount St. Helens eruptions, which was tiny compared to what Yellowstone is capable of, or Mount Pinatubo in the Philippines from the 90s which was much bigger than Mount St. Helens, but it was tiny compared to the size of Yellowstone. And so when we look at Yellowstone and the potential, this is the view that we get. And as we're coming quickly to what I was supposed to be the original time, even though we started 15 minutes late. So I'm going to blast through some of this. But the Yellowstone eruption size from, again, the 2.1, the 1.2, and the 600, and this should be about 630,000 year old eruptions are gigantic. These are huge, greater than 1,000 cubic kilometers. Again, Mount St. Helens is 1/4 of a kilometer, Pinatubo 5 cubic kilometers. So these are three massive eruptions with some bigger ones that have taken place in other areas. But we have to really be paying attention to the size of this caldera, from a policy perspective and a scientific perspective, because it does have major ramifications. And some of the ash distribution that we see from Yellowstone is pretty spectacular. So here, again, Mount St. Helens, this is the actual distribution of ash from Mount St. Helens. These are the three large eruptions, plus there's another volcano in this beige dotted line here from Long Valley and Long Valley caldera in California that's superimposed on here. But these are three massive eruptions. Again, these are the ash deposits. This is not the distribution of ash. This is where we can go and actually find ash deposits. In fact, I've led several field trips into southern Death Valley down here in California to look at the thick ash deposits that are present there in southern Death Valley that come from Yellowstone. They're pretty spectacular. So the potential consequences of a large Yellowstone eruption are fairly significant. Here, just for reference, this is the Grand Canyon of the Yellowstone River. These are some of those ash deposits. Again, these are some fairly large trees just for scale, but these are huge, thick deposits of ash and pyroclastic material from these large eruptions. And one of the more interesting study, which has really kind of reigniting a lot of conspiracy theory and communication issues with respect to Yellowstone, was a recent modeling study done by Masson and others back in 2014, where they modeled the distribution of ash, the thickness of ash deposits from a potential Yellowstone eruption based on what we know. And you can see that the ash deposits pretty much cover most of North America, skewed to the east because of the prevailing winds coming off the Pacific Ocean. But you can see there are vast areas, including some fairly important agricultural areas, that are going to be completely covered and devastated by ash. So if there were eruption, at least this is the model, and this really jives with what we can see from these past eruptions. So it's absolutely something that we need to pay attention to. And ash is a huge problem. I'm going to really quickly read through this again for the sake of time, but again, millimeters of ash, we're talking transportation issues, electrical systems can be impacted, respiratory impacts are a problem. I don't know if you recall, if you might recall, there was an eruption in 2010 from an Icelandic volcano that Brian, after you can pronounce this properly, but I can't exactly pronounce the volcano name, but in 2010, it erupted, a really small eruption, but the ash that was ejected into the atmosphere disrupted European, like basically any travel between Europe and North America, much of Europe's air travel for about a month. And that was a tiny, tiny eruption. So in the middle part of the US, this would be huge for the agriculture. Thick deposits of ash will completely disrupt, all of our modern systems of sewage and water treatment and distribution. They could impact building integrity. The mass would impact, building structure. North American transportation would be completely devastated. That's almost certain. And it would probably have global air transportation and communication issues for, a long time, as well as, and something I'm not even going to talk about, global climate. This would be a huge issue for global climate. We saw global climate impacts from the Pinatubo eruption. We have great views of what happened during that, again, relatively small eruption. So this would be absolutely a huge impact for North America if it were to erupt. So let's come back to, that's a bunch of the science, and I ripped through a bunch of that again with our late start. I ripped through a bunch of that science, especially some of the more recent science, really quickly. But I wanted to get to, okay, what are the odds? Well, the odds of an eruption, as I said earlier, tomorrow are zero. All right, we already know what some of the precursors are, but the odds are about 1 in 700-ish thousand, or if you want to use percentages, about 0.0001%. And just for reference, I threw a few things on here, including some boring, some morbid stuff at the bottom. But lightning, for example, you're more likely to get struck by lightning than Yellowstone erupted. Okay, which again is not something we really concern ourselves on a daily basis, but when you're out in an open field during a thunderstorm, you're darn right you think about it. And so when you're sitting there in an active volcano, you're darn right we should be thinking about this system. And just in contrast, the Lotto Max, 1 in about 33 million. All right, but we still play the lottery because those are much worse odds. And another thing, the odds of you, probably not you unless you're really relatively young listening to this webinar right now, but I think most of us are past the median NHL age maybe listening to this, but the odds of playing one game in the NHL are about 1 in 2,500. So, and I won't go through all the morbid horrible things about, transportation, the risk of transportation. So the odds are extremely small, which is why in my original title, I said maybe, but not likely. Are they zero? Absolutely not. And should we be putting money and resources into understanding Yellowstone and actually communicating about the potential risks of not just Yellowstone, but volcanic eruptions? We should absolutely be doing that. Should we be putting out YouTube videos that say we're all going to die tomorrow from Yellowstone? Absolutely not, because that's not going to happen. Some of the things that are going to happen are things like earthquakes and other systems. But the question is, how do we know all this? How do we know there is magma down here? And I just wanted to come back to this idea that we absolutely know this. This is actually a little bit more detailed scientific view of that picture that schematic diagram that I showed, showing that there is magma down here. And this is looking at the change in P wave velocity, so seismic wave velocity, as it goes through the crust. And basically the way you read this is warm colors on the diagram mean slower waves, mean hotter rock or potentially molten rock. And as it turns out, there's molten rock in this part of the world right here. Okay, but we can see there's a big region of hot rock or partially molten rock beneath Yellowstone as we take these progressive slices through that. Again, you can see 2, 5, 8, 14 kilometers, which is how we develop this little cross-sectional view of what the magma below Yellowstone looks like. And so there absolutely is magma below there, so we have to be paying attention to it. And how much of it? There's a lot of magma below Yellowstone. There's a region, again, single digits mostly, 5 to 15% melt in this. This is an odd looking diagram. So we're looking north. Here's our green, this is our park boundary in green projected on the surface. This is the caldera boundary in blue up here. Those are those two domes, the Mallard Creek, excuse me, the Mallard Dome and the Sour Creek Dome. And here's depth, okay? So again, we have, you know, between 5 and 15 kilometers, we have a huge region of partial melt, okay? So again, this is not 100% melt, this is partial melt, but that represents about 200 to 600 cubic kilometers of molten material. And if you recall, some of those large eruptions were in the, you know, the 1,000 cubic kilometer range, and Pinatubo was, you know, Pinatubo was 5 cubic kilometers. So we're talking very, very large volumes of partial melt, which is, again, one of the reasons why we need to be paying attention to that. I should also point out that we also have indications of the hydrothermal activity. That's this gold box right here. These are some of those hot fluids and things that, not things, but hot fluids like water and carbon dioxide that are also in part responsible for some of the activity in Yellowstone. We can measure heat flow. Again, I'm going to skip through some of this because I've already gone past and I want to get to some of the communication issues and answer questions, but we can measure the heat flow. Abnormally high heat flow, not only throughout the eastern, Snake River Plain, but certainly over Yellowstone. It's a big hot region, and I'll come to a news article that kind of makes a point of this soon. Again, this is just Yellowstone Lake, high heat flow. I'll skip through that again. The other thing that we can measure that's really cool, here is the Yellowstone caldera. Here are those domes that you can see. This is actually a living, breathing caldera. We can actually measure using GPS uplift and subsidence within the caldera over approximately 30 years, 35 years, where we can see that there are periods of time right here between 87 and 95 where there was subsidence or down dropping happening in the caldera. And then through 95 to 2000, there were areas of uplift. And we have another period of down drop, but in fact, from about 2015 to about 2020, we have another period of uplift that's happening in it. So the surface of this caldera is rising and falling as activity, both hydrothermal and magmatic, is happening below the surface. Again, and in some cases, we get some very rapid uplift. A couple centimeters per year doesn't sound like a lot, but we're talking about massive areas of uplift that are happening throughout this region. Okay, and for reference, think about having somebody sit on your chest, how hard it is to breathe with just that amount of weight on your chest. Now we're talking about raising a huge swath of the Earth's crust by several centimeters per year. That's a big deal, which really again indicates that we've got both magmatic and hydrothermal activity beneath there. One of the things that in terms of thinking about Yellowstone and thinking about whether we should be paying attention to whether some kind of eruption, whether it's maybe not a huge catastrophic eruption, but maybe it's another lava flow or a hydrothermal explosion, are what are called earthquake swarms. There are literally hundreds of earthquakes all the time in the Yellowstone area, but every once in a while we get these these earthquake swarms that are concentrated and that happen over a very abbreviated period of time. And here's one from 2008 and 2009 that I'll show a little bit more detail here in a second. And there's also one that happened in 2020. So these are some of the precursor triggers that at least get scientists' ears and eyes peaked a little bit. And brains going a little bit, thinking about, okay, is this something we should be paying attention to in terms of, again, probably not a catastrophic eruption with something small like this, but maybe a small hydrothermal eruption. But these are, so just for reference, these are all of the earthquakes that occur in the Yellowstone area. Again, thousands upon, on average, about 200 earthquakes a day, small ones mostly, but thousands upon thousands of earthquakes every year. But there's some of these earthquake swarms that are concerning. Here's the 2008-2009 swarm, and so this is. Again, it sounds like a long period of time, but it's actually over a period of just about 2 weeks. So from late 2008, December 27th, to early 2009, what we're looking at is this big swarm. Here's Yellowstone Lake. We're looking top-down view, Yellowstone Lake, and this is mislabeled. This should be X and that should be X prime, but we're looking at a swarm of earthquakes that you can actually track from the 27th of December, where we have these earthquakes that are down low, to later on where some of the earthquakes are moving upwards, which is kind of tracking something, whether it's magma, maybe it could have been magma, it could have been fluids as well, moving below the surface. So these are some of the realistic precursor events that we would be expecting before some kind of eruption, okay? And again, it's the rate at which those swarms are happening. We have tons and tons of earthquake activity all the time. Here are some of those periods of uplift just for reference, but we have some rates of activities. Okay, the 2008-2009 swarm, the 2020 swarm, where the amount of earthquake, again, we're talking about hundreds of earthquakes, happen over a much more rapid rate. And again, these are some of the precursor things that we would hear about as the public, from scientists thinking about, okay, we might be expecting something that we want to be concerned about. So let's back up. Again, I blasted through a bunch of that stuff and trying to get through stuff, but do we know that Yellowstone is going to erupt with catastrophic global consequences? It absolutely is, almost with 100% certainty going to erupt with global catastrophic circumstances. Is it going to happen in our lifetimes? Almost certainly not. Is it going to happen in our grandchildren's lifetimes? Almost certainly not. But if it does happen in our lifetimes, we're going to get lead up warnings like those earthquake swarms, heat flow measurements. We're measuring a bunch of other things, the uplift through time that are giving us indications. So kind of one of the points of this was, how do we communicate this? How do we deal with this? And I have a few examples here. This first one right here, drilling in Yellowstone could save America. A plan for generating carbon-free energy, that's awesome, and staving off a caldera explosion. Okay, this is from the Wall Street Journal just a few days ago, all right? Written by a scientist, but the main crux of that title, you read staving off a caldera explosion and you think, oh, wait a minute, is Yellowstone going to erupt? No, it's not going to erupt. But the whole crux of this was actually thinking about tapping into the geothermal energy that that is possible by using Yellowstone. Much like Iceland uses a tremendous amount of geothermal energy, we could be using the same thing in Yellowstone. A little bit more challenges, national park situation, but nevertheless, we could do that. Another great example, NASA's ambitious plan to save Earth from a supervolcano. This is from the BBC 2017. This followed a NASA report written by a NASA scientist who is responsible for doing things like rovers and things like that, but wrote a plan to think about cooling off Yellowstone to save us from a supervolcano eruption by pumping water down there, which is complete poppycock. It's completely ridiculous. And this is coming from NASA. So we need to be careful, and I'll point this out again in a second. We need to be careful. It's not always necessarily, we might be trying to grab attention, but that article, I read the article, it's actually pretty crazy to think that we could cool this off using water. It just would not work. We could certainly use water to generate geothermal energy. Fantastic idea, completely fantastic idea. But to think that we would cool this off to prevent an eruption is crazy. And then the other big question that I have is, how do we compete with the very clickbaity titles of mainstream media or social media as scientists to garner attention? Again, coming back to my first point about the title for this talk, which was abbreviated for distribution to the public. How do we compete with that? I've been teaching about earth science and specifically about Yellowstone. I generally hit about 500 to 1,000 students a year for the past 10 years-ish plus. And so I've directly impacted about 10,000 students over that 10-year span. And then you got YouTube, 3.4 million views in less than a year, with some crazy conspiracy theories about Yellowstone erupting, which mostly are incorrect. 6.4 million views in the last 5 months, all right? 46,000 views from a crazy unexplained mysteries website in the last 17 hours. 5 times more people watch this than the students I've chatted with or had courses with and the public I've engaged with over the last 10 years of my life talking about Yellowstone. So how do we compete with that? This is a fantastic one too, just as an aside. Yellowstone National Park just revealed that something is happening right now inside Yellowstone. Notice the big, beautiful picture of a bison. The bison are migrating. They do it every year. Almost every single year, the folks at the National Park Service say, look, when it starts to get cool off, the weather gets cool, the bison, they migrate, they go elsewhere. And so there's and they do it in herds. So there's a mass exodus and people in the park freak out and the conspiracy theorists love it. Unexplained mysteries. It's not really unexplained. It's just migration. But again, 50,000 views in the last 17 hours. I took this screen cap this morning, so 17,000 views in the 17 hours, 50,000 views. So it's fantastic, fantastic viewership. But how do we compete with that communication? So is Yellowstone going to erupt? Yes. Is it going to happen anytime soon? No. So yeah, I'm going to leave it there since I've reached my almost hour here, again, starting late, but I want to open it up to the participants for questions, whether it's about the science or comments about the communication. Did you come here because of that very enticing title, or was it some other reason? So thank you, and again, sorry for the very, very late start with the technical issues, but yeah, Q&A. Let's have at it.
Oh, fantastic, Jeff. Thanks very much.
So I just saw in the chat, what are the sources of the relatively high radioisotopes, and they add something to heating in the structure also for the source of the isotopic. Did I show something with isotopes in there? Those isotopes are mostly coming from the natural rocks. Those are common isotopic systems that we get, that we actually use for dating. In fact, both of those systems, the potassium argon system and the uranium lead system, are both isotopic systems that we use in earth science to actually acquire radiometric ages. And so with the relatively large volumes of felsic material, that rhyolitic material in the area, we're going to have elevated levels of the uranium and lead for sure. Oh, cool. Awesome. That is very cool. I'm so glad you came to do that. So those are natural systems that we shouldn't be worried about. It's not something dangerous. They're actually quite useful. But because we have so much rhyolitic magma in the area, we're going to have higher levels of those, both radon gases and those isotopic systems. So also in the chat, I see, why are the Columbia rivers so displaced from the Yellowstone? That is a fantastic question. So that's a big area of active research. Oh, cool. Oh, well then, yeah, awesome. So that's an area. I'm going to scroll back to that diagram of the overview picture. So why is there such a big displacement? So this is the fascinating area of active research. We see the vents. This is where the source of those Columbia River basalt magmas outpoured from. So they cover a very broad area, including actually there's evidence for those basaltic lavas reaching the Pacific Ocean. But most of the activity came from here. There's a few interesting ideas about what is going on beneath that part of the world about 25 to 15 million years ago. And part of the issue is this subduction zone right here. Recall, we've got the Pacific plate, and in fact, let me grab my pen. So we have the Pacific plate right here, and this is North America. So the Pacific plate is getting shoved underneath the edge of North America right here. Okay, so our edge volcano, our Mount St. Helens and things are right here. That shouldn't be a point like that. That was just my weird, my pad kind of not behaving. But what we have is a situation where our mantle plume has to rise up and actually sorry for the tear. It's harder writing on this pad right now than actually a whiteboard. So my diagrams are not great. But this plume right here had to interact with that subducting plate. And I looked at some recent research that where it's thought that the actual plume ripped the actual plate open, caused a tear in that slab. And so in doing so, there may have been some deflection of the plume itself or of the magmatism as that plume rose up and engaged. It's a really complicated problem, but an area of active research. This interaction between plume and subducting slab in the Pacific Northwest. So I don't know that we have a firm "this is why" answer at this point, but again, that's maybe part of the reason. It's a great question. And I don't know if people can not type questions or just ask questions out loud or not on these or not, but oh, there's Q&A. Oh yeah, sorry, I saw the same thing twice, but if you wanted to unmute and ask a question, that would be totally cool as well.
Sorry, Jeff, there's no functionality for unmute.
Oh, okay, cool.
People have to post into the either the chat or the Q&A.
Oh, no problem. Okay, so I saw Clinton just asked a question. Is it possible that the hotspot has now intersected a thicker continental crust and will be only appropriate further east? Well, that's a good question. The thickness of the lithosphere is relatively consistent in that part of the world. I would have to double check whether we have some major thickness variations off in the east, but I don't think we have any major thickness issues. And in fact, it's thinner there than it is further to the west. And so, and part of the reason why, and this is to visualize this, part of the reason why you have the propagation of the hotspot to the east is because, I'll just use this part, part of the world, sorry, I touched the wrong button here. This part of the world over here. Part of the reason is because North America is moving to the west. So this is the crust. That's an N, sorry, North America. And the plume is, again, relatively fixed down here. So as that's east and that's west. So the plume itself isn't really migrating. It's the crust. So in fact, your question is still reasonable, because if this was thicker, it may become problematic to generate partial melting there, although it could actually, in fact, make it slightly easier to have partial melting there. But I don't think that's the case. We have a relatively uniform thickness, at least, in that part of the world, for several tens to hundreds of kilometers, which is kind of the region we need to worry about when we're only moving, again, this is only moving, 2.5 centimeters per year. In this direction. So, over 500,000 years, we're talking kilometers of motion, tens to hundreds of kilometers of motion, not like, thousands. Good question. Oh, there's another one. Okay, we've seen, yes. That's a really great point that you make, Clinton. We seem to act like the eruption will be one and done, but if an eruption would occur over several thousands of years, perhaps we'd never recover. That's a very realistic situation. And in fact, when we go and date some of the materials from the last major eruptions, and I don't have any data in my presentation. I might have some at the very end, but I don't think I have any data in my presentation. I don't think I included that particular slide. But this is absolutely not a one and done situation. The eruption, especially if we're talking about a major eruption, one of the big catastrophic eruptions, those are happening over thousands of years. They're happening over long enough periods of time that we can date individual deposits and resolve those using our geochronologic techniques. And so it's not a situation, even if we think about Mount St. Helens, like Mount St. Helens erupted over several days, the main part of the eruption, and even continued erupting into the mid 1980s, with smaller dome building events inside Mount St. Helens and eruptions. That happened with that tiny eruption. It happened over, a decade, let's call it. And something like this would absolutely happen. It would not be just a one-shot deal. It would be, hundreds, if not thousands of eruptions over hundreds, if not thousands of years. And yeah, it would be tough to recover from that. Would it be, so it's an interesting, again, this is an interesting, public policy kind of type question. Would it be like extinction of humans? Probably not. Humans are pretty smart. We can engineer for a lot of stuff these days. But would we lose a lot of life? Yeah, there would be we would lose a lot of people just locally for that matter. But then the issues with respect to food distribution and growing food would be hugely problematic, as well as, global travel and climate change. But would humans go extinct? Almost certainly not. We're pretty good about that. Elon Musk would save us. He'd just shoot us all off to Mars and we would be fine. But it's certainly something that we don't want to ignore. I think that's really kind of one of the key things is, we shouldn't just ignore this. We should actively research it. We should, devote, funds towards, places like the U.S. Geological Survey and the National Park Service to be able to, research this and pay attention to it and monitor it. But we don't need to be sitting on the edge of our seats in fear and panic. Again, that's a little bit too much. The Discovery Channel movie was, it was realistic but exaggerated at the same time. I mean, there were, again, a lot of the visuals, it's tough because, and again, especially even 15 years ago, the budget for Discovery Channel videos was certainly not like what the budget for Star Wars is, or something like that, or a big Hollywood film is to generate like good effects. So they used a lot of things like actually some of the video footage from the Mount Pinatubo eruption, for example. But you know, I think there's a lot of predictions that, you know, you have to be able to take predictions with a grain of salt, because they are just that, they're predictions. We do our best with predicting. Again, you don't want to send people into panic mode, but yeah, it was pretty well done. I'll just say that there was some liberties, but it was pretty well done.
I'm going to have to interject now,
Sure.
Jeff, because we are 3 minutes to getting cut off at the back end of this session and having those hiccups at the beginning. I don't want the same thing to happen to you at the end. So yes, thank you very much. And thank you to the audience. We've answered all the questions, I believe. And
yeah, I'll continue typing.
Okay, perfect.
But yeah, while you talk. Yeah.
And we can continue to answer questions that come in after this presentation. And the presentation will be posted. It's being recorded and will be posted to science.carleton.ca, the Science Café series section of the website. So thank you. And I am going to I'll leave this open until 3 o'clock, and
sure.
And then we'll hard stop, I do think.
Okay. Let me get to the Canadian question.
Okay.
There's no Canadian examples. We have North America has got its fair share. We've got not only Yellowstone in Wyoming and Montana, we have the Long Valley caldera in California, which I had a little bit of diagram from that, but there's also the Valles caldera in New Mexico. There are 3 major, Yellowstone sized, volcanoes in North America. So nothing in Canada, but even Canada would be a huge problem, even if Yellowstone erupted. But things like, even the volcanoes in Western US and in British Columbia are not, they would be large, but not nearly the same scale on like the volcano explosivity index that, is 8 and above for things like Yellowstone and Long Valley. But yeah, so we're pretty safe in Canada, at least from the immediate vicinity types of impacts. Mont Tremblant's totally dormant, so we're pretty good.
Okay, is that it? I think there's no other questions that I can see.
Cool. Well, thank you, everyone.
Thank you very much again, and until next time.